Good afternoon. In the last class, we have seen ARM modes and ARM states. There are three ARM states. They are ARM state, second thumb state, third Jajali state. These are because of the instruction set. Instruction set, there are three different types of instructions in the instruction set. They are 32-bit instructions, 16-bit instructions, and 8-bit instructions. 32-bit instructions are executed in the ARM state. 16-bit instructions are executed in the thumb state. 8-bit instructions are executed in the Jajali state. This is because if you make instructions this way, we will have higher code density, because most frequently used instructions can be made 8-bit or 16-bit. Less frequently used instructions or rarely used instructions can be made 32-bit wide. That is how we can achieve high code density. And to execute these different size instructions, we have three different modes. ARM mode, in which 32-bit instructions are executed. Thumb state, in which not mode, in thumb state we instructions with 16 bits are executed, whereas in Jajali state it is not available with all the processor cores. If the processor implements Jajali state, only then it is available. If it is there, it executes 8-bit instructions. Next, we have different states. There are 7 different states. They are user not states, modes. There are 7 different modes: user mode, undefined mode, system mode, supervisor mode, interrupt request mode, fast interrupt request mode, abort mode. And we have seen the status register, CPSR register. And CPSR register, with the use of CPSR register, the programmer, the information of the current program is available. Information of the current program is found by using CPSR register. Now, if you look into this bits 0 through 4, and these bits are called mode bits. These bits, 5 bits tell about the mode of the processor. If these 5 bits M4, M3, M2, M1, M0 are like this. This is M4, M3, M2, M1, M0. If you read 10111 in these 5-bit places, then the currently processor is in abort mode. Currently processor is in abort mode. Next, if you read 1001 in this place, in this 5 bits place, then processor is executing fast interrupt request. For do so, it went to which state? Which mode? Fast interrupt request mode. And if the processor is in interrupt request mode, then these bits will be like this: 10010. Supervisor mode 10011. For the system mode, we have all 5 ones. For undefined mode 11011. User mode 1000. In the user mode, we have all the user written programs will be executed. And in the yesterday's class, we have talked about different modes in which what different type of things will be executed. For example, undefined, if processor encounters instruction which is not defined in the instruction set, to handle that, it goes into undefined mode. Like that, we have all these modes. Abort mode, if processor tries to access location which is protected, then it goes into which mode? Abort mode. Next topic is it is not new topic. It is continuation of the same architecture of ARM7. Programming model. Programming model means what are the registers available when the processor changes its state from not state, it's a mode from user to FIQ or IRQ or SVC or undefined or abort. So these are the resources available within the processor when the processor changes its mode from one mode to another. Let's say the processor has this available resources when it is in user state, user mode or system mode. User mode, system mode shares these registers. If the processor is executing the program, user written program, then it will be in user mode, right? User mode. And when it is in the user mode, it has these registers to use. It has all these registers, R0, R1, all the registers, including CPSR register. Whereas, because of fast interrupt request, let's say processor switches from user mode to FIQ mode, let's say. When the processor is in FIQ mode, then it has only this many registers. It has R8 register, R9 register, R10 register, R11, R12, R3, 13, R14, and we have other register called SPSR, saved program status register. Here SPSR stands for saved program status register, and we don't have CPSR register in FIQ mode. Processor doesn't access, it doesn't have CPSR register in FIQ mode. And also R15 is also absent when the processor is in FIQ mode. And all these registers, see, this R8 register and this R8 register are completely different. They are physically separate registers. Means if you have some contents in R8, when the process switches its state to FIQ, when the process switches its mode to FIQ, where R8, if you store something in R8, this changes will not affect the register which is present in the user mode. This R8 register means all the names are same. This R8 is different from this R8. Otherwise, if you want, you can add some suffix R8 underscore FIQ. If you want, you can name like this: R8 underscore FIQ, R9 underscore FIQ, R10 underscore FIQ. These are separate registers called banked registers. In the same way, in IRQ, we have only, when the processor is in IRQ, we have these separate registers: R13, which acts as stack pointer, R14, which acts as link register, and also SPSR register. This SPSR register is completely different. All the names are same. If you want, you can add suffix underscore FIQ. You can think like this: SPSR underscore IRQ, SPSR underscore SVC. You can add suffix. The suffix name would be the processor mode. And see, in the IRQ mode, the processor has only 1, 2, 3 registers, new separate registers, and if it wants to use, it can use all these registers R0, R1, R2, R3, R4, which are available in user mode or system mode. If the processor wants to use, it can use all the registers R0 to R12, but the problem is, if you have stored anything in the user mode, and if you switch the state to IRQ, if you make changes to those registers, let's say R4 is having the value 20. In the user mode, you have stored some ALU result, which is 20 in R4 register. And because of interrupt request, the processor goes into IRQ state, IRQ mode, IRQ mode. It doesn't mean R4 register is not available in IRQ mode. It is available in IRQ mode, but you are using the same R4 register which is having 20. If you store some other number, let's say 40, the 20 will be erased, 40 will be stored. If you switch back to user mode, then R4 no more contains 20, it contains 40, which is changed in IRQ mode. Are you following? Means you are using the same registers which are present, same physical registers which are present in user mode in IRQ, user state in IRQ state. These are the registers available in user state. Is it mode or state? Sorry, mode. I'm confusing every time. It is user mode. These are the available registers in the user mode. When if you want to use, you can use these registers in IRQ mode also. Sorry, IRQ mode also. But the thing is, you are using the same physical registers present in user mode. Are you following? But in FIQ, these blue shaded registers, they are not same as this. R8 is not same as R8 here. This R8 in FIQ mode is not same as R8 in user mode. These are separate registers, although their names are same. These are separate registers. For example, R8 contains 20, and when you switch the mode to FIQ, if you store a 40 in R8, and if you go back to user mode, this R8 contains 20 only, because this R8 is different from this R8. Whereas R7 here, they are same. This R7 only available in FIQ mode also. If you want to use these registers, let's say, if you want to use these registers R0 to R7 in FIQ mode, they will be used in FIQ mode. The same registers R0 to R7 will be used as they are, right? If you want to use these registers, which is already, these registers are already having some data, then what we have to do is push this data to some stack. The data which is present in these registers, push the data present in these registers to stack, then use the registers in FIQ mode, these registers R0 to R7. And when you switch the state of the processor from FIQ mode to user mode, pop the data which is present on the stack to these registers. That is how you cannot lose any data which is present in these registers in user mode if you want to use these registers in the FIQ mode. There is no problem with this R8, R9, R10, R11, R12, because a new copy of these registers are available in FIQ mode. If you want to use R8, R9, R10, R11, R12 registers, there is no need to push the data present in these registers when you switch from here to here, because this R8, R9, R10, R11, R12 are different registers, although their names are same. That's why if you want, you can add some FIQ to differentiate this register from this register. And in our ARQ, we don't have any registers. If you want to use them, you can use them, these registers, but after pushing the data present in these registers to stack, and you can use those registers. When you switch from IRQ back to user mode, then you can pop the data present in the stack. Like that, we can use these registers without losing any contents. And totally, how many registers we have in the register bank? Register bank is nothing but group of registers. So in user mode, we have this many registers R0 to R15, totally 16 plus 1, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37. Totally we have 37 registers, 37 different registers present in the register bank or register file. And when the processor is in user mode, these are the available registers. When the processor is in FIQ mode, these are the new copy of these registers. These are the new registers. And if you want, you can use R0, R1, all these registers also. But before using them, you have to push the data present in these registers to the stack. and pop the data when you go from FIQ back to user state. Same is true for all other modes. And see, when there is switching in processor mode from user to FIQ, let's say, or from user to IRQ, whatever, what happens is the contents of CPSR will be stored to SPSR register. The contents of CPSR register will be stored to SPSR register. The contents of program counter will be stored to R link register, which is R14, which is link register R14. Now some process happens in FIQ mode. When the process completes, the processor moves from FIQ mode back to user mode. Then SPSR contents are copied back to CPSR. Link registers are copied back to program counter. That's what happens when the processor changes its mode from one to another. Right? Let's see. ARM programming model has, let's read these slides, as totally 37 registers. Just now we counted and it is 37. 37 registers in its register bank, which are segmented for different modes of operation. User mode register set is shared by the system mode also. The same set of registers are used by processor in user mode as well as in system mode. Okay, these are shared by both the modes. Each of the remaining privileged modes has a set of banked registers which are active. Banked registers means what are the banked registers in FIQ mode? R8, R9, R10, R11, R12, R13 stack pointer, R14 link register, SPSR. These are banked registers, means these are new copy. R8, this R8 is not same as this R8. The changes that are made to this R8 will not affect this R8, whereas the changes that are made to R7 in FIQ mode, that certainly affects R7 in user mode, because the same physical register is being used in FIQ mode if you are using it, and so on. Only shaded, blue shaded registers are the physically separate registers. All other registers, it doesn't mean in SVC mode you cannot use R1. You can use R1, but you are using this R1 only. Remember that. Next, bank registers for a particular mode are physically replication of few of the user mode registers along with a saved program status register shown by shaded in the figure. If the processor mode is changed, for example, from user to FIQ mode due to occurrence of hardware interrupt, the bank registers R8 to R14 from FIQ mode will replace the corresponding registers in user mode, but the remaining user mode registers R0 to R7 can still be used in FIQ mode after saving the previous contents. Is this completed? Right. It means registers R8 to R14 of user mode are unaffected by this mode change. The purpose of these banked registers is to reduce the content saving overhead. Why we have these new registers here? Suppose if there are no new registers here, let's say R8, if you want to use, you are using R8, same R8 here also. Let's imagine we don't have these registers, new registers. Then every time if you need to use any register, you have to use the same register which is in user mode. So if R8 is already having some data, then you have to push the data to the stack before you use it and pop the data which is present in the stack after you went back to user mode. It takes some time. To save the time, we have this banked registers. That is the point. Whenever processor changes its mode from one to another, this banked registers avoid this delay in processing. So the purpose of these banked registers is to reduce the context saving overhead. There is only one context saving overhead, means when you change the state from one to another, there is no need for you to save the contents, because there are new registers available in the other mode. There is only one dedicated PC and one CPSR for all the operation modes. We don't have program counter which is banked over all the modes of the processor. When a mode is changed, the program counter and CPSR contents are saved in the link register. Program counter and CPSR contents are saved in the link register and SPSR respectively. Means the program counter of the current mode will be changed to R14 of that mode. CPSR of user mode will be saved to SPSR of that new mode respectively. Means PC contents will be copied to R14 of that new mode. CPSR of the current mode, that will be contents of CPSR of the current mode will be copied to SPSR register of the new mode. Means what all data is present in CPSR, that will be saved to SPSR of the new mode. And when it is going back, the SPSR contents are copied back to CPSR. The same thing is true for R14. R14 which is linked register, those contents are copied back to program counter of the user mode. Next, interrupt handling, interrupt and exception handling. This is new subtopic. What is interrupt? Interrupt, if a processor is doing its normal duty, regular duty, executing a program, if some hardware wants its interruption, hardware wants to communicate with the processor, then hardware issues an interrupt to the processor, then processor attempts that request which is issued by some hardware, and after executing it, it goes back to its normal, it resumes its normal execution. That's what interrupt is. Exceptions, there is no big difference between exceptions and interrupts, because in ARM both are processed exactly in the same way. CPU becomes forced to stop the normal execution to respond to the exception or interrupt at a faster rate. ARM core supports 7 exceptions, including the hardware interrupts. Interrupt handling, this is one subtopic. Interrupt is used to get service from CPU by generating a request only when it is required. There are two types of attempting the request of interfacing devices. That is, one is by polling, other one is by interrupt. Polling is not that effective, so interrupts are used. Two types of interrupts are hardware interrupts and software interrupts. You can have two types of interrupts. One is hardware type, other one is software type. Hardware means for the processor we have many peripherals like timer peripheral, ADC peripheral, pulse width modulation. There are so many peripherals. Let's say you are using analog to digital conversion. When analog to digital conversion is completed, then you can issue some interrupt. You can interrupt. Then what should happen when analog to digital conversion is completed? You can write that code in the interrupt handling, interrupt service routine. The requests made by the peripherals, they are called hardware interrupts, because each and every peripheral is one hardware unit. The requests made by the hardware peripherals to the processor are called hardware interrupts. You can interrupt the program, normal regular execution of the program, through software instructions also. That is called software interrupt. These are the requests not made by any any hardware peripheral, but it is like one, it is software interrupt is like one instruction, like move instruction or add instruction. We have one instruction first, we have a few instructions for software interrupts. So totally we have these two varieties, hardware variety and the software interrupts. Hardware interrupts come from the peripherals or IOs connected in a system, and software interrupt by executing an interrupt instruction. So when any interrupt occurs during program execution, there is some problem with the camera. When any interrupt occurs during program execution, CPU completes the current instruction execution. Now saves the return address in the defined portion of the memory called stack, and then it responds to the interrupt. So when interrupt request is made, the processor completes executing that instruction and it saves the address of the next instruction in the stack, and it goes to interrupt service routine, the address location where that interrupt service routine is written. The control of the program execution is transferred to the corresponding interrupt vector address. Each interrupt is given one address. Means when that particular interrupt is made, then the execution goes to that location called interrupt service routine. There we write the program. When that particular interrupt is requested, what should happen? That will be written in interrupt service routine functions. You have aware of these functions called interrupt service routine functions, ISR functions, right? That is this thing. Each interrupt is given one fixed location, particular location, and the program that you are writing in interrupt service routine, that program will be stored in that particular location corresponding to the interrupt. At the end of ISR execution, the return address is retrieved back from the stack and control resumes back at the address where it had left. After executing the interrupts, it goes back to its normal execution. How does processor knows where it stopped executing the normal program? Because it has stored the last executed instruction in the stack. Okay, it knows that way, and by retrieving the information back from the stack, it resumes its normal execution. ARM core has two hardware interrupts, FIQ and IRQ. It has two hardware interrupts, FIQ, IRQ. FIQ interrupts are low latency, having high priority over IRQ interrupts, but those are considered also as exceptions, since core follows the same process of handling both interrupts and exceptions. ARM processor doesn't see any difference between hard interrupts and exceptions. It processes both exceptions and interrupts exactly in the same way. An exception, now exception handling. An exception is any condition, an unexpected event or error that needs to halt the normal execution of instructions. See, interrupts are the requests made by hardware, like timer. When timer overflows first time or second time, each time timer overflows, you can have one interrupt. Or when timer value is equal to some fixed value, you can have one interrupt. Interrupts are like this, whereas exceptions are not something like this. Whenever unplanned situation happens in the processor, that is termed exception. An exception is any condition or an unexpected event or error that needs to halt the normal execution of instructions. So that is called exception. ARM core considers hardware interrupts under exceptions. So hardware treats interrupts also as exceptions only. It supports 7 exceptions as follows: reset, data abort, prefetch abort, FIQ, IRQ. These are actually hardware interrupts, and these are exceptions. Abort, prefetch abort, data abort, reset. These are actual exceptions. SWI means software interrupt, and undefined. These two are hardware interrupts. This is software interrupt. Others are exceptions, but processor handles all these things as exceptions only. Each of the ARM exception is associated with certain operating mode and causes the ARM core to enter to that particular mode automatically upon exception entry. See, these are the different exceptions we have. When any exception is occurred, when some exception occurs, then processor automatically goes to some mode to execute that, to handle that, or to execute that exception. For example, hardware interrupt request is made, fast interrupt request is made. Let's say right now processor is executing some task in some program. Because if any program is executed, then it is in which mode? User mode. When this fast interrupt request is made, then the core goes into FIQ mode from user mode to execute this fast interrupt request. If it is IRQ interrupt, normal interrupt, then it goes from user to IRQ mode. If it is a software interrupt, then it goes to some mode where these software interrupts are executed. In the group of exceptions, there are supervisor calls such as reset and software interrupts, undefined instruction trap, memory access failure such as data abort and prefetch abort, and hardware interrupts such as fast interrupt request and interrupt request. Next, as more than one interrupt may occur simultaneously, exceptions are prioritized in the priorities list given in the table. When there is a possibility that more than one interrupt can be occurred at the same time. If that is the case, then we process the interrupts according to this priority given here. Exceptions: reset, undefined, software interrupt, prefetch abort, data abort, IRQ, FIQ. These are the exceptions that we have. In IRQ, we have so many interrupts. In FIQ, we have so many interrupts, and so on. That for that you have to look into interrupt vector table. Interrupt vector table, you will find the complete list of all the interrupts. Here we are just seeing different types of exceptions, different category of exceptions. See, when reset is given highest priority 1, means at the same time reset exception and undefined exception are occurred at the same time. Which will be executed first? Which will be attempted first? Reset will be attempted first, and then when it is completed, it goes to processor, looks at the undefined, like that, software, and so on. This is the priority list. And see, when this, let's say, when reset instruction is being executed or undefined instruction is being executed, I bit in the CPSR, I means interrupt request, 0 means disabled, 1 means enabled. See, let's see, when software interrupt software interrupt request is made, then the processor goes into supervisor mode. Software, to execute the software interrupt, the processor goes into supervisor mode, and when it is executed, while it is executing, the F bit means what is this F? Fast interrupt request. 0 means enable, 1 means disable. 1 means normal interrupt. I bit means what is this I bit corresponds to in the CPSR register? I bit is for normal interrupt, low priority interrupt. F bit means what is that F bit? High priority interrupts. 0 means enable, 1 means disable. Software interrupt. And now look at the difference between software interrupt and the FIQ interrupt. Between software interrupt and FIQ interrupt, which is having high priority? Software interrupt and FIQ interrupt. FIQ interrupt is having priority 3, whereas software interrupt is having priority 6. So while software interrupt is being executed, if FIQ interrupt is request is made, then it stops executing the software interrupt. It accepts the FIQ interrupt, which is high priority interrupt. After executing FIQ interrupt, it goes back to software interrupt. So when software interrupt is being executed, so it tells, it keeps this FIQ bit in 0 as 0, because 0 means it is FIQ is accepted, means FIQ requests are accepted, because SWI is having low priority 6, whereas FIQ is having high priority. So this bit is kept 0, whereas I bit means low priority, because software interrupt is also normal priority. Means what it says is processor allows fast interrupts, whereas processor doesn't accept any low interrupts. The low interrupts they should be waited until processor completes this software interrupt. Only then it accepts the next low priority interrupt. When SW interrupt is being executed, at the time processor is ready to handle or accept the fast interrupts. That's why this bit is 0, this bit is 1. The same is true for all others. Next, when any exception occurs, the control transfers to the corresponding vector address. Vector address means every interrupt is given one address. In that location only the program will be stored. Interrupt program will be stored. In the vector address, certain branch instructions would be written to access actual interrupt handler or ISR saved at the different location. It is required as the vector address are sequentially separated by 4 bytes only when only one 32-bit ARM instruction can be written at each of it. 4 bytes. Why 4 bytes? Because in ARM state, the instructions are of 32-bit wide. 32-bit wide means you need 4-bit separation. The I and F bits in the control field of CPSR register are disabled in combination while handling the exception. Disabled means processor is not ready to accept any interrupts when it is already executing the interrupts. All the ARM exceptions are executed in ARM state of the core. ARM has 3 states: ARM state, thumb state, and George state. Whenever any exception is occurred, all those exceptions are executed in which state of the processor? ARM state, not in thumb state, nor in George state. It executes the exceptions only in ARM state. If the control is there in the thumb state, it has to switch back to ARM state to handle the exception. Currently, the processor is executing 16-bit instruction. Means what is the state of the processor? Thumb state. Now, during that time, exception has occurred. To execute that exception, it has to move to which state? ARM state. Because in ARM state only, all the exceptions are executed. After executing that exception, it comes back to its thumb state and it resumes its execution, normal execution. Exception entry. Upon exception entry, the following changes will take place. When an exception occurs, ARM core goes through the following sequence of operations. It changes to the operating mode corresponding to the particular exception. Means it changes the operating mode. Operating mode means, suppose if the exception is software interrupt. If software interrupt is request is made, it changes to which mode? Right now, the processor is in user mode, let's say. To execute software interrupt, it goes to supervisor mode. It changes to the operating mode, means it changes to supervisor mode to execute software interrupt. It changes to FIQ mode to execute fast interrupt request exception, like that, corresponding to the particular exception. It saves the return address. It saves the return address. The contents of program counter R15 in link register of the new mode that we have seen. Our program counter will be stored in link register of the new mode. It saves the previous state of the core, the content of the CPSR to SPSR of the new mode. Disables IRQs by setting bit 7 of the CPSR, and if the exception is reset or fast interrupt, disables further fast interrupts by setting at bit 6 of the CPSR. Program counter is loaded with a vector address to begin executing the relevant exception handler. See, the type of every exception is having a unique address. That address is that address. So when you write a program for exception or interrupt in the ISR interrupt service routine, that program will be stored in that particular location. So program counter is now loaded with the vector address of that corresponding interrupt. Now execution goes back to that location. So when after executing the exception or interrupt, now these are the steps that happens. The user program is resumed once the interrupt handler execution is completed. The following steps are doing so. The saved context must be restored back from the handler's stack. See, if there are any registers contents, if you have some data in the registers which are pushed to the stack, okay, they are retrieved now after executing the exceptions. When you are coming back from some other mode to user mode during that time, or as a first step, this is what happens. The data which is present in the stack, that is popped and stored in the corresponding registers. CPSR must be restored from appropriate SPSR. So SPSR is having the status of the current program. Now that is copied back to CPSR. During exception entry, CPSR contents are copied to SPSR of the new mode, whereas after executing the exceptions, the SPSR contents are copied back to CPSR. The program counter must be restored back from link register. See, during exception entry, program counter address is loaded to link register. In the exception exit, the link registers are copied back to program counter. What are the steps that we have done during the exception entry? The same steps are done in the reverse manner after the exception is executed. So here we stop.